Hi everybody, it's Dr. Chabot, and in this video we are going to talk about the idea of resistivity, resistance, and Ohm's law. So let's start by imagining that we have our path, our conductor, a little bit of wire through which we want to have our current flow through. So we have some cross-sectional area A of this bit of wire, and we have some length L, and we're going to be applying an electric field E that's going to then cause our charge flow. And so we're going to make an analogy here. So we want to just recall one of the basic kind of cause and effect equations in physics. This one would be the idea that we would have the force is equal to the mass, let's call that the net force, mass times the acceleration. And in this scenario, right, we like to think of the force as the cause and the acceleration as the effect. The mass we've sometimes just taken for granted, this idea of its measure of inertia, but really you can also think about it in this context as, something that hinders the effect. Right? So this here is going to be something that can inhibits the effect. Right? So the larger the mass, the lower the acceleration. And so in an analogy here is that we have the electric field, and that's going to then create some current density. Let's call that current density J. So remember, this is our current density, which was just our current per area, right? And in the direction of charge flow. And then we have to talk about, well, what might inhibit that, right? The electric field creates the current density, and there's going to be this inhibitor, and the inhibitor here is going to be what we call the resistivity. So this is going to be the resistivity. So this is, again, the cause is the electric field. The effect is the current density, and the inhibitor is the resistivity. Now I'm using, it's rho, and I'm putting a little subscript r just so we don't get it confused with our densities. So rho sub r is not a density, it is the resistivity of a material, and it's a property of the material. And that's going to be because we have, used the current density here. And so then that was going to allow us to talk about just the current per area. So we're kind of taking some of the geometry out of this. So it's a property of the material, and it's a measure of how much that material inhibits charge flow. So a higher resistivity means the material inhibits or limits the current flow more. And a lower resistivity means that it's a good conductor, right? The lower the resistivity means it's a better so-called conductor. The unit of resistivity is one that we'll come to in a second once I relate it to the idea of resistance. So this is going to be our resistivity. We have another cause and effect equation, which is more famous, which is Ohm's law, and it really can come from this idea of resistivity. So if we go ahead and we think about this equation here, and we just put in what we know that it is. Recall here that electric field is going to be equal to volts per meter. So if I just have some set length here, then my delta V is going to be equal to the electric field times that length, right? And that delta V is essentially the hill that I'm creating between the plus V and the minus V, and the electric field is flowing downhill in this scenario. So that's always something to keep in mind. And the slope of that is my electric field. So the smaller over that delta V occurs over a smaller length, then that's going to be a steeper hill, a bigger electric field, a more shallow, and that's going to be a smaller electric field. So E is equal to delta V over L, and as I've already said, our J is equal to our current over an area. So we can put all of these together and we can end up with the following. So I can go back to the original equation and I can say E equals rho J. That's going to give me delta V over L equals rho, and I'm going to keep remembering to call it rho sub R. So again, we don't view it as a density, times I over A. And so we then end up with this relationship, which is that delta V is equal to rho sub R times the length of the wire or the object over the area, all times I. So I'm going to box that. And this is just another way of looking at cause and effect, right? Delta V is our cause and I is our effect. This is our current. And this is what inhibits the charge flow. So this is hindering the flow of charge. And so what we actually see here is that this is what we're going to call the resistance. So let's go ahead and define that quantity here. So we have now resistance. I'm going to call it capital R. And that resistance is going to be something that depends on the material, because it does involve the rho, and on the geometry of the material. How much of it do you have, right? Is it a long, skinny piece of wire? Is it a thick, wide piece of wire? And all of that is going to depend and change, the properties of what inhibits the motion, so how much there is. And so then we end up with our kind of famous equation for what we call Ohm's law, which is really kind of just the definition of resistance, which is that delta V is equal to R times I, which is more commonly written as IR. And so we can say, right, that the resistance is essentially related to the relationship between the cause and the effect. Something is ohmic if the R is constant, with delta V and I, meaning that if I was going to plot I versus delta V, that I would get a straight line of sorts. So all of these would be ohmic materials. And if I wanted to say plot a non-ohmic, something non-ohmic might be like an LED, kind of stays off for a while, and then it goes up like so. So this, let me redraw that. This one kind of would be like this, and this would be a non-ohmic value. The resistance can still be calculated at each point, but it does not have a constant resistance. Okay, and then the last thing that I want to mention when we talk about resistance, resistivity, and Ohm's law is fundamentally what's going to be causing some of this resistance. And so I'm just going to put down here one last note that sort of fundamentally what's hindering this charge flow is that the resistance is dependent upon a lot of factors, but it can be thought of as in the big picture as a measure of the amount of collisions, dependent upon the number of collisions that the free electrons have as they move in the electric field. And each collision transfers some energy. So each collision transfers some energy. And so we're actually then going to be losing some of our energy because remember, recall that delta V is equal to energy per charge. So these collisions are a way in which these electrons are actually going to be losing their energy, and in this case it's their electric potential energy that they're losing as they have these collisions, and then that hinders the amount of flow of charge that you can have. So that's a good thing to keep in mind as we're trying to navigate and eventually looking at circuits that have resistors in them, and in a future video when we talk about the power dissipated in a resistive circuit. All right, so I hope that this was a good introduction to resistivity, resistance, and Ohm's law.